This video is about repairing portable solar generators such as the one you see in this picture. This is a very common type. I have several of these, or if possible salvaging them if repair is not feasible. Now it's also going to be sort of a teardown video because I do like seeing what's inside of electronics. In fact, teardown videos are some of my all-time favorite videos to watch. And seeing what's inside of these is pretty interesting, I think. And if you like electronics, it's always interesting to see what's inside. Now this particular unit that I'm using for the video is working now. When I got it, it was totally dark. It was not working. It was a brick. But now most of the outputs are working. The AC output still does not work because it has a blown MOSFET, and I don't have any replacement at the moment. But hopefully that can be replaced later. So I'm going to use this unit as the example. I have several. And I'm just going to go ahead and take it apart and work on all the different steps for fault finding. Now I'm going to talk a little bit also about the internals in the unit, because these are, if you're trying to learn about electronics, and I consider myself always learning, these are really actually great for learning basic things. You know, assuming you already know what a resistor is, a diode, a transformer, so forth, you want to kind of go a little deeper. This is kind of a safe and, I won't say cheap, but a really real-world way of learning about electronics. Now, I don't know how long this video will be, but I'm going to go ahead and start the disassembly. I might have to break it up into multiple videos. I don't know if there's an upload limit. And I'm pretty happy with the way these are constructed. They're very easy to get into. This is the type of construction method I prefer. I call it a stack method. Especially a stack of layers, and then there's 4 or more bolts, large metal bolts coming down through the top. And I really prefer that method of construction. So let's get the bolts out. Make sure they're all the way loose. Now when I take something apart, I find it helpful to take photographs, and it helps you remember where everything is. And let's go ahead, lift the top off. Now on the right hand side there will be fans, and those are usually glued in. Now I've already cut the glue, so I found it easy, but they're on the right side and the wires aren't that long, so you got to be careful. Just lift the top off. Okay, I zoom the camera. Now I'm using a cell phone camera and the zoom is not so great. You have to pause the video in order to zoom it. I have a better one coming in the mail. I don't know if it'll help, but we'll see. So this is a pretty neat design. You have 2 main heat sinks here. I believe this is the output stage for the inverter. It's kind of hard to tell. This is the input stage, and then there's also some other MOSFETs and diodes and whatnot for other parts of the circuit. And then they've just bridged it together with another piece of aluminum. I like that design. It's a neat way of just increasing the heat sinking, the thermal heat sinking, without, really, it's not very complicated. It's just a piece of metal with some holes in it, and it really does add value. Now there's no heat sink compound here, but you could put that there. I like modifying and tweaking things like this. Now, I don't remember which way the fans blow by default. Generally, I've heard you want the air blowing in because that generates turbulence and leads to better cooling. If you have air blowing out, you're drawing air in and it creates a laminar flow, for example, around these capacitors, and you get hot spots. Now, of course, that's really being nitpicky, but if you're into that sort of thing, I generally reverse my fans to blow in, unless there's a reason to have them blowing out. They don't move much air anyway, and this thing doesn't generate much heat the way I use them. I don't stress them that hard. I'm not gonna, especially when I've been modifying them. I don't want to run them too hard. It's a plastic box. I mean, you can't expect much out of it. So I'm going to remove this heatsink here, and we can take a look at the components and what you need to check for when you first open one of these up to see some faults are obvious right away. So we'll get into that next. Now I've got a new tool here. It's the Bosch right angle drill. Been wanting this for many years. Now this never used it before. This is massive overkill. They don't generally thread these aluminum heat sinks, and so the first screws that were in here I had to replace because they were just totally tore up. Now this is really overkill. I don't know that this is the right tool for the job, but I want to try it out, so we'll give it a shot. I know it has the power. Oops. Oh, yeah, it looks like these are not as beat up. The screws are in a lot better shape, the new screws. Yep. Yeah, massive overkill, but I had to try it out. I haven't been able to use this thing just yet. Yeah, I love Bosch tools. Alright, got that out. And there you go, aluminum comes off. Alright, so next let's take a look inside the circuit board. I'm going to try to angle this better so we can get a look inside. Okay, so when you first open the unit, again, be aware that there are high voltages present, and you don't know if the circuit was designed to bleed these capacitors down or not. I don't actually know, and I'm careful what I touch. So the first thing you want to look for when you open it up is any signs of obvious damage of any kind. High on the list would be water, corrosion, water infiltration, corrosion damage, salt air, any evidence that there's salt deposits, water deposits, or corrosion. Because when you see that, pretty much you got a dud. It's unlikely you'll be able to revive a unit like that. Now, I have received at least one of these that had bad water damage. It appeared that there was some sort of water infiltration. Who knows? It could have got rained on or left at the ocean. Who knows? And I was not able to revive the inverter stage on that one. The next thing you want to look for is any sign of burning, heat, melting, and you want to look for a black smudge by all the MOSFETs. Now, the MOSFETs are simply electronic switches that can be switched very rapidly, and you can do various things with them. This unit is full of mini MOSFETs. It has quite a few. And you also want to look at the capacitors to see if the top is bulged or if they've vented their electrolyte. Now, these caps look just fine, and you can see there's actually a three-way mark there, and that's a perforated area where if these caps explode, they'll open up and vent their contents. But these caps look fine. And in fact, this whole board is half decent looking. You never know what you're going to get. So this one, this whole board is actually in fairly decent shape, considering I didn't pay a whole lot for it, and it was in broken, not working condition. So the first thing I would do after looking at all of that is you'll need a multimeter. And even a cheap multimeter would do. You don't have to buy a $3,000 multimeter or even a $100 multimeter. So I'm going to show you next what I usually probe without touching anything else in here and changing anything. What I would usually probe in here in a solar generator to find out what's going on. So I'll do that next. Now I realize that the footage here is not very clear. I'm hoping my new camera that's coming will be better. But I will show a close-up of the board later. Right now I'm just going to do the probing with the multimeter to see what's going on. So that's next. Okay, I've adjusted the camera a bit. So just for reference, this is the front part of the unit where the display is. This is all the wires feeding the display. And this is the back part over on this section. And these are the sides, just so you have a reference of what you're looking at. This is the top of the display right there. And I really should get something to point with. So that right there is a display, that white line there. It's the LCD display, LED display. And this is, I believe this is output stage. It's hard because they have these, I believe, silicone boots covering up the MOSFETs. And I don't want to mess with any of that because it works. As far as I know, these are all good. So on the left side, you can see that there's a couple of very large wires coming up. Well, not very large, but they're the biggest here. This here, and there's a red one right there I'm touching. And obviously those are the high current wires coming from the battery pack. I mean, they have to be. When you see wires like that, you know. So what I'm going to do is take my multimeter. And I use a cheap multimeter. I have about 8 of these, and I just love them. It's this GE model GE2524 multimeter. I love this thing. You can even calibrate it. And what I like about it is when you turn it on, it stays on until the battery dies. I hate those auto power off things. Why they don't give you the option to override that, I don't know. Or set a longer override, I don't know. So I'm going to use this basic multimeter. And I don't know if I can get the multimeter in the frame or not. We'll see. Let me see if I can do that. I think that would be a good idea. Just slide this over. And if you want a multimeter stand, I just use the old rolls that packing tape come on. And I put my multimeter in those. Let's see if I can go over this way instead. So I put the multimeter over here. So I put it on the 20 volt scale. And I've got 2 probes, positive and negative. Now it's important to note what range you're on, or I should say what function you're on, before you start probing. Now I'm on the voltage, DC volts, 20 volts. Wow, you can actually see that on the camera. That's amazing. But there's not a lot of room here. I'm having, I need to get over to the left side, so let me see if I can get a little more room. So, yeah, you can just barely see. So on the left side we have these large wires, and they come up to some very large, I guess they're lugs or mounting places on the motherboard or main board. And obviously you would expect that if this unit was functioning to some degree, there would be a voltage of approximately 11.1 volts on those terminals. Now this system has a 3S lithium-ion battery pack. I think it's 10P, so 10 parallel. They're just 18650 cells. So you would expect a voltage of around 11 volts or so. So the first thing I do is I would probe those and see what am I getting. So let's go ahead and probe it. And we're getting 10.86 volts. So what does that tell us? What that tells us is that since most of these have, well, I hope they do, have a battery management system, so that's a board that sits on top of the battery, and it controls the output and monitors it. The potentially volatile, or they are actually volatile, lithium-ion cells to protect them from damage, such as catching fire, getting too hot, or getting outside of operating parameters. That tells me that that system is switched on and it's outputting power. Now that's a 90% guess. There could always be an edge case. Now when I got this unit, actually that was not the case. Remember, I've done have this open and worked on it. When I got it, that was not the case. There was no electricity being supplied on these big wires. So that told me right away, it's no wonder the unit was dead. But that's the first thing you would do. Now, let's make the assumption that there is no voltage on these wires, because that was the original case when I repaired this unit. So what you would see is probably like a half a volt or 1 volt, or you might see 0 volts on the multimeter. And what that would tell you is that the MOSFETs on the BMS, on the battery pack, are switched off and are producing, there's basically no voltage coming through. It could also mean the battery's flat dead, but I don't know if that would happen or not. I don't know what would happen in that case. So when you see something like that, the first thing you want to do is you're going to assume the battery's dead or not putting out power. And that could be for a variety of reasons. So the first thing I'm going to do is essentially defuse this device by removing the power source from it. I want to remove the battery pack, completely isolate it from the system, and essentially depower the board so I can probe it. So I'm going to do that next, and I'm going to try to get some better footage of the left side now that you've seen the whole board, of the left side where I'm actually working. We'll see how that goes. I don't know how well this camera's going to handle it, but I will try. So that's next. Okay, so now I need to remove the large screws that are holding in the holding these large cables on. I would generally disconnect the red one first. That's positive. I hope you can see what I'm doing. Oh boy. Alright. So I'm going to put the bolts over here. Disconnect the positive. So there's the positive right there. I'm going to disconnect the negative next. Okay, so now the battery pack has been completely removed. And make sure you don't short them together. Even though it has a BMS, you don't want to risk that. That's a very high-powered pack. It's capable of delivering probably over 50 amps, and that would create quite a spark. And you want to be careful not to let these touch the circuit board anywhere that you don't want voltage going. So now the unit is basically disarmed. However, there are other connections. So you have these up here, and I can't really show you those, but those multicolored wires that were going up to the display, I'm going to disconnect those as well. So let me show you that next. Okay, so these are the display cables, and one of them actually comes from the BMS on the battery pack. The other one goes to the computer on the main board. So I'm going to disconnect those carefully. And you saw it blink there. So now the unit is totally diffused. There is no connection to the battery at all right now. So now what I want to do is I'm going to remeasure, or I'm going to measure again the battery pack output. Once again, I'm getting, okay, it's going down. So notice how the multimeter is going down. See, you can see it going down there. So what's happened is the BMS has switched the battery pack off. What does that tell us? Well, what it tells me is that this cable here has some kind of communication with the main board. and the BMS will not operate unless it's in communication with the microprocessor on the main board here. Now I don't know what it's doing. It's possibly just pulling one of these down to ground or something, or there's a serial bus. I don't know, because there's so much here you can learn, and I don't know everything, so I'm just guessing. But now this board is totally defused, and there is no power going to it. It can't be any, because other than what's in the capacitors. So now we can begin testing some various things on the board using a multimeter to try to determine what the fault is. So that's next. Okay, I've switched my multimeter to the 200 ohm scale here. That's ohms is a measurement of resistance, and of course if I cross the multimeter leads like this, touch them together, I get basically nothing, 0.5. Who knows how accurate that is? About a half an ohm, but who knows what it actually is. But that's extremely low, and effectively it's a short circuit if you see that. So what I'm going to do is I'm going to probe the terminals input where the battery is connected to see what the impedance is. So let's do that. So I'm going to go ahead and probe. You can see the multimeter probes coming in from the left side of the screen. Okay. Effectively it's effectively, you know, infinite resistance. It's hard to get a good connection sometimes. Yeah, it's basically giving me an infinite reading. So let's try it again. It's hard to get a good connection. Yeah, that's a very high impedance. Hopefully I'm not misreading it. Let's try it again on the 2000 ohm scale. So on a lower scale it's not doing anything, but if I switch it to a higher scale, I mean, you're getting a very high, I think that's a really high reading there. So let's see if I cross the meet. Yeah, so effectively what I'm seeing here is on the input where the batteries go, there is no short circuit. It's pretty much open. Now what you'll often see on this type of board is you'll see a very low reading in ohms. So it might look something like on the display, if you cross the multimeter leads, you might see a 0, you might see maybe a 10, maybe a 12 or something. And in the case of this particular unit, that was what was wrong. So one of the MOSFETs here had shorted out, and it actually was causing the input to be short. It was an input MOSFET. And the source and the drain of the MOSFET had shorted across the positive and negative rail. And what happens is when that's a short circuit. So next I'm going to zoom into the left side where I found that fault and show you what I did to check. But before, I'm going to probe some other locations. So another place you can probe is you can probe the AC input. So I'm not showing you, but the AC outlet, the 110 volt AC outlet. Be very careful doing this. Only do it if you know what you're doing. Probe across hot and neutral, which is the two main prongs on the outlet, and see if it's low impedance. If it is effectively an open circuit or high impedance, then it's probably okay. You can also do the same thing to the charge input. Now I happen to know that this cable here is the charge input from the solar. So I was curious and I probed across that. And you basically get nothing. Yeah, so it's basically open circuit, as it should be. Now on this unit I probed everything and I wasn't able to get any reading. And that's how it should be. You don't want to see a short circuit on any of the inputs or outputs outside the case, because that's a problem. Something is shorted out. It should never be that way. So next I'm going to zoom in on the left side and I'm going to show you what I did to check where the main power input is. Okay, so I've tried to zoom in and I've increased the lighting so you can see better. Fun fact, all the lighting here, and there's several of them, is actually powered by solar generators, including one that's just like the one I'm working on here. And the phone itself is being powered by another one. Everything here is powered by solar that you're seeing, including the camera. So you start seeing some bawdry here. I use the multimeter probe to point with. You can see a little bit of hot glue there. That's where the fuses used to be. I ripped those out. I bent them back and forth till they came out. And these yellow wires go to upside down automotive fuse that I hot glued in upside down. So yeah, not a professional repair, but it's good enough. This got the unit working for me part of the way. After I cut the MOSFET out of the circuit, this is how I repaired it, or at least got it working. Now there used to be two small fuses there, right here where I'm pointing. Very small fuses in parallel, 25 amps a piece if memory serves correctly. That's going to give you about 50 amps more or less if you parallel fuses. However, I found an interesting condition, and I've seen this before. one of the fuses had blown, the other one had not. And it was kind of confusing. Now the way you check these fuses is I usually have two little bits of exposed metal on the top. And I'll show you that in just a moment. Incidentally, I managed to find one of the blown up fuses that I ripped out. So I'm going to try to show it to you. There it is. It's a 30 amp, so it was 60 amps. That's the top of the fuse you're looking at. And in the middle, you can see there is no fuse. It's gone. So that got blown up. And of course, the blades that stick out of the bottom of the fuse were broken off, because that's how I got the fuse out. I ripped it out. So at the top of the fuse, let's see if this will even focus. There's two holes, and there's little pieces of metal there. I'm going to point at one of them, right there. Usually you can get your multimeter probes in there and you can measure the fuse with a continuity check to see if the fuse is blown or open circuit. So in my case, I found an interesting condition. One of the fuses was blown, the other one was not. So what happened is the BMS, there was a short circuit condition, and the BMS tripped extremely quickly before the second fuse could blow, because both fuses, of course, are not identical and they have different values, and they actually are not quite the same. So it just so happened the first fuse blew, the second fuse did not, leaving a single 30 amp fuse in place. However, once that happens, as the BMS goes into safety lockdown mode or brick mode, apparently that's the way it's designed, and I don't fault them for that, but it did brick this device. So there was a short circuit event, and it blew one fuse and then tripped the BMS before the other fuse would blow. However, in the process of my troubleshooting, I blew the second fuse, which is common for me. I blow a lot of fuses, make a lot of mistakes. So that's why I had to remove both fuses, and I hot glued in this wire here. Well, actually soldered and hot glued it. And then I hot glued in an automotive style fuse. So the BMS tripped. That means it's got intelligence there, and it knows it's got overcurrent protection, and it has other protections as well. What that means is that the BMS worked as intended, and it's well designed. So that's actually a good thing. The downside is it bricked the unit. There's no way to recover from it that I know of without opening it up. So what I did is, when I found that the fuses were blown, I realized there's a short circuit on the input. I then removed this board from the housing and began probing all around looking for the fault. And I managed to find the fault. So the next thing I'm going to do is take this board out, and we can look at it, look at the different components, and how to check for a blown MOSFET, or a shorted MOSFET, I should say. So that's next. So I hope you're enjoying this video so far. It's probably going to be a really long one, but there's a lot here, and believe me, it's not even half. I could make it even longer probably, but I'm just trying to get through it. I wanted to explain what a BMS is. So a BMS means it could mean two things, in my opinion, because I have a second meaning for it. So here's a battery pack from another solar generator. Actually happens to be one of my favorites, but I was not able to finish troubleshooting it, and so I took the battery out because I don't want a battery sitting for years on a shelf and something that doesn't work. I just took it out. You can see there's quite a lot going on there. Wow, the lighting is not so good. Okay, I'm just gonna... Anyway, I can do a separate video about this later, about a BMS. The BMS is essentially this circuit board on the top. This is a 3S10P battery pack. These are fiberglass plates, I believe. It's very, very nice. I really am impressed. These solar generators usually cost $300 or $400, $200 to $400, and I'm finding when I open them up, I'm actually kind of impressed. You know, you can knock the Chinese all you want to. Those people that work in the factories, I really feel for them. They put out some good work. They get criticized a lot, but they're just ordinary people trying to earn a living. They're not responsible for their government. And I got to say, they do pretty good work. The design is okay. Now, I don't know if this is an American design. Almost certainly it was built in China. Now, I can go over this in a separate video and show you all the different parts and what they do. I can explain 90% of what's on here. Of course, some of it's a mystery because, like, for example, this IC here, I don't think it has any labeling on it. I don't have a surface mount microscope, but I'm almost certain I know what it is. So 90% of what's on here I can explain. That would be a separate video, but this is a BMS. This is a computer board that sits on top of the battery pack, and it monitors everything. And if there's a problem, the BMS is supposed to protect the battery. It's a battery management system. Now, I'm a fan of what's called a battery monitoring system, which means that it just monitors and it reports back. It doesn't actually balance the cells or anything like that. So that's the other type of BMS. So that would be a separate video. That's just going to make this too long. So the BMS, I'm referring to the computer board that monitors the battery pack and protects from overcurrent, undervoltage, overvoltage, short circuit, and overcharge, things like that. So just a little bit of extra information there. So next I'm going to lift this board out, and we can go ahead and get it out and look at it closely. Okay, so to get the board out, I'm going to disconnect. This is the DC charge or solar input. I've already took this color cable out and the other color cable, rainbow cable. This is, I believe, from the microprocessor on the system board. And you've got the AC one here. Now I'm being very careful where I put my fingers. Be very careful because there could still be high voltages on this board. And I really like the design of this system, of this solar generator. It's, once you learn how it works, it's easy to get it apart. And the circuit board should now lift straight up. And you want to try to remove any wires and don't pull too hard on them. Alright, and the circuit board comes out. So that's the main board. You can call it the motherboard, system board, main board, whatever you want to call it. Now, as soon as you do that, you can take a look at the bottom of the circuit board for the first time. Now, this one's clean for the most part. It's a little dirty. And yes, that's an automotive fuse I soldered in earlier for a test attempt. Now, a little trick if you're troubleshooting a board like this one, and the lighting is terrible. I have much to learn about using a camera. Yeah, that's a little better. You'll notice there's writing all over the bottom, and what that was is that's me when I'm probing the board. I write on it what it is, because when you turn the board over, it's so confusing, and you forget where each thing is. So as I probe each thing and find out what it is, I mark it. So on the left there, you can see I wrote the ground symbol, because this is negative, and it's they reverse. If you turn the board upside down, depending on how you're looking at it, it can be backward. It can be very confusing. So this board was relatively clean, and there's no sign of burning or scarring, blown tracks. And the tracks are these little paths that are running everywhere. Those are very thin copper, and in a short circuit event, in many cases, these will vaporize or partially vaporize. But this is a good board. It's in good shape, considering I didn't pay a lot for this unit, and it was damaged. So it's not too bad. So let's put the board aside and look at what was underneath. So now you can see what's underneath. And that yellow thing is a battery very similar to the one I just showed you. This is the front panel. That's the cigarette lighter outlet right there. This is the main battery positive cable coming around from the battery. I'm sorry, it's not the main, it's the secondary. This is the secondary that feeds like the cigarette outlet and the USB ports and that sort of thing. These are the main ones that feed the inverter, the high power board. These also, in this unit, also provide the charge current, charge delivery from the solar or the AC. Well, not the AC, but the... Actually, that's incorrect. Yeah, all the charging is done through these wires here, to the best of my knowledge. Now, over here is a 2.1 millimeter jack I installed. And I realize it's hard to see. Oh, that's not so good. Right there is a 2.1 millimeter jack I installed myself, so that was a modification aftermarket. Right here is interesting. This is a bracket for an XT60 connector, which apparently was never implemented. In electronics, you'll see a lot of things where, that could be XT90, I don't know. You'll see a lot of cases where something's not implemented. It was intended, maybe at some point in the design stage, maybe the engineers intended to include it in the product, but later on they never did. Or maybe it's there because other products, there's variations of a product line, and some of them have it, some of them don't, and it's cheaper to make them all the same. So that's what that is. So that's the battery, and it has a date of 2019. And I don't know how to, the date is backward to me, that's not how I write it. So I'm guessing that's October, the 30th of October 2019 was when this was manufactured. And you can see it's got hold downs on either side. You got fiberglass sheets, and you can see the 18650s poking out right there. Once again, it's kind of hard to see on this camera, but you can see the 18650 cells right there. And when you open a unit like this, you always want to pay special attention to the battery. Is it damaged? Because these cells are absolute bombs. And if you have a damaged pack, you know, one of these cells, just one of these cells can get so hot it does a thermal runaway, a cascade scenario where it gets the adjacent cells hot, the cells right next to it, and then they in turn thermal runaway, and then this whole pack can just go up in flames. Now, I'm very impressed with the way it's constructed. A lot of these units that I'm opening, this is fiberglass, I think. See, that stuff isn't free. And they went out of their way to really make sure this is a safe unit. And in fact, so far, that if there's a simple short circuit, on the input stage on the inverter, rather than just blowing the inverter stage and throwing an error code, it just shuts the whole unit down. They're so paranoid that this unit would be a liability to the customer. Not consumer, but customer. We're not consumers, we're customers. We're producers. So here you can see, I'm going to have to keep lifting this up. That, where my thumb is, that's the XLR jack. There's just a circuit board there, and I don't know what that component there does. Maybe I can look at that later. There's a Zener diode there and a voltage regulator or something. But that's where the solar panels connect. This is where my solar panels connect, where my thumb is. That's where I put the 2.1 millimeter jack in. So, spoiler alert, I've already looked at this battery thoroughly, and there's nothing wrong with it. I've had it out, I've tested it, and there's nothing wrong with it. So I think I'm going to do a separate video some other time showing how to look at these packs very closely and troubleshoot them, because honestly that's a whole separate topic. But you should always pay special attention to the battery. And you know, in this case I was able to determine the battery is just fine. There's nothing wrong with it. It's a healthy battery. I don't even think it has a lot of cycles on it. I don't think these units had a lot of cycles on them. I think they just had a short life. So now let's turn our attention back to the main board, which has really got most of the stuff going on. Now, you might be surprised to learn this here, the display on the front, also has a lot of circuitry on it. There's a lot of chips. There's a lot going on here. It's probably even a whole video of itself. Now, I do want to warn you, if you take this front panel board out, it has two chip LEDs. I believe these are called cob LEDs. They're right here, and they're behind these lenses. These are extremely dangerous to the human eye, naked eye. Okay, so if you take this front panel out and disassemble it, use extreme care and extreme caution if you power this board up, because one of these LEDs comes on without the lens, the diffuser right here, and hits you right in the eye when you weren't expecting it. You can damage your retina. Now that may sound ridiculous, but it's the truth. And I've already had run-ins with LEDs like this before. High power LEDs are it's almost like a solid state laser, and you have to be very careful. So just be aware that that's the type of LED that's used here. They're not meant to be used with the naked eye. There's a diffuser here. That's this plastic lens here. So just be really careful. Eyes are really valuable and you only get 2 of them, so don't mess them up. Okay, so next I'm going to go back to the system board. I'm going to try to make the video clearer, and we're going to take a look at that to see what can you do to troubleshoot and to fault find. So that's next.